And now kind of jump into the highly accelerated stress testing. The one thing is that this 85-85 test, if you really have, you don't even need to have a hermetic component. So I don't mean that these are slow only for ceramic or packages or metal lid components or these kind of. It's also modern overmolded packages. So even they have organic material, which we discussed two lectures ago quite much, that they will absorb moisture and the moisture will change their properties, but still the moisture diffusion is so slow that the let's say the testing time becomes so long that it's not useful. So if you need to run a test which takes 6 months and the acceleration factor is not high enough, then of course that's not very efficient way of testing. So therefore, people started to develop new types of tests, and these go under the name of HAST, highly accelerated stress test. So what does it mean is that our target is to get conditions where we can accelerate the failures or failure mechanisms by increasing the temperature even up to 150 degrees centigrade, but we still stay below 85 degrees relative humidity. So in a minute, I will be showing how these kind of conditions can be achieved. It's not that complex in principle. And these are now, maybe I should have put here again this stage gate slide, which we have used several times, so you still remember the shape of that. Maybe I will just quickly draw it. So our stage gate graph. So we had here in y-axis we had the reliability, and now, for example, our HALT testing was here at the first part. So this part here. Now this HAST testing is basically, the point is also here. So more we want to, let's say, compare things. We want to check the design rather than getting the actual lifetime. But maybe this HAST testing is more also part of this, let's say, lifetime verification rather than HALT. Even this is also, let's say, over accelerated, but sometimes we can still, let's say, confirm that the failure mechanisms are not drastically changed. So once more, the main point is to compare materials, compare designs, but you can also use this one for, let's say, wear out mechanisms, which is in contrast with the HALT testing, typically. So as we know, you have seen this, let's say, Arrhenius equation already several times, and maybe in your basic physics courses or material science courses, you have also seen so-called fixed laws of diffusion. So diffusion coefficient, which tell us how fast the atoms are moving, then this diffusion coefficient is also Arrhenius dependent. So it means that diffusion occurs exponentially when temperature is increased. So that is basically the acceleration here. So once more, we want to keep this one constant, but we want to accelerate the test by increasing the temperature. Okay, so now if we jump to this page, so maybe you remember I showed you, maybe it was in the second or third lecture, I showed you this, let's say, the effect of activation energy. So this is now the EA in the Arrhenius equation exponent, which tells us how strong is the effect of temperature on that specific failure mechanism. So again, please keep in mind that now always our primary assumption is that when we accelerate, we increase the stresses, we still keep the same failure mechanisms. And then everything what we, let's say, now discuss is valid. If the failure mechanism is changed, something else is happening if we over accelerate, then everything is kind of the whole ground of this approach is kind of destroyed. But now we know that for these kind of humidity-induced corrosion, like here the formation of dendrites between two conductors, or here we have some kind of most probably thin migration corrosion between the leads of an electronic component. We know that the let's say the activation energy is typically in this order of magnitude, roughly 1 electron. And now if we go back to this curve, what does it mean? We can have a rough estimate on what is the acceleration factor. So if we would now take that, okay, on average use environment, we have average temperature of 40 degrees centigrade. So then we would be here. This would be our lifetime in the average conditions. If we take this 85 test, then that should be, where's 85 is somewhere here, I think. Oh, sorry about that. So we are about here. So in 85 test, the test would take 10 power 5, so 100,000 hours. What is that? 100,000 hours is roughly 10 years. If we are able to increase the testing temperature to 150 degrees, okay, this is an extreme temperature, but then the test time would be, what is that, 2,000 hours or something like that, and maybe even less than 2,000 hours. Meaning that now we are talking about testing time of 1 to 2 months. And those two would simulate a lifetime of 10 power 7 hours. So 100,000 million, 10 million hours. So it's hundreds of years if I calculate correct. You are better in math. So it means that if the failure mechanism stays the same, this curve here shows that how, while keeping the relative humidity constant, just by increasing the temperature, we can correlate the use conditions, testing conditions below 100 degrees centigrade and testing conditions above 100 degrees centigrade, how these should match together if we do not over accelerate, if the failure mechanism stays the same. So that is the basic idea once more. Okay, maybe I will go back to the laser pointer. So then, because of that, people have developed these highly accelerated stress tests. And this is now just a table from another IEC standard, which is from the same, let's say, 68-2. It was 67, now it's 66. So this is just for the specifications of pressurized chambers. And let's see again if I maybe, not sure. I hope that you now see also this, let's say, table. And if this is maybe a little bit confusing and maybe also somewhat small, but here in the let's say upper row we have the relative humidity, and in this first column we have the temperature. If we, for example, I'm not sure if you can see it, but here we have 130 degrees centigrade, and here we have 85% relative humidity. So this is quite typical HAST test, or 120. And then from this cell, we can see that what is the extra pressure needed. So now these are megapascals, so meaning that this value here is 1.7 bars, and this is 2.3 bars or something like that. So that's the amount of pressure we need in order to keep these kind of conditions. And then the other number here states again the saturation temperature. So if we are running our test in 120 at 85% relative humidity, then we need at least 1.7 bars extra pressure. And if any of the surfaces are the temperature is below 115, then we get condensation. So at this temperature, then the relative humidity goes to 100%. So this is just the point. So in the standards, you have these kind of let's say tools for analyzing the temperature humidity relationship and required pressure. Okay, let's jump back. Okay, again, please shout if this HAST slide is not visible. So basically, this is just taken from the JPCA standard, so Japanese standard. Just the definition. What was the original purpose of this HAST test, and how you should utilize it. So maybe once more to point out this part here. So mainly the purpose is to compare, check the designs, compare materials and these kind of things. If you are sure that you are not affecting on the failure mechanism, so the acceleration factor is understood properly, then you could also use it for lifetime estimations. But otherwise, it's more like halt testing. Okay, so that's just the point. Want to highlight several times so everybody really remembers the main restrictions and main assumptions when you use it in different ways. Okay, the requirements for the let's say the equipment itself, these are quite the same as what we had in the 85 test standard. So you need to be able to let's say start it up in a controlled time frame. You need to run it for constantly without any interruptions. Now in the 85 it was up to more than 2 months, but now here it says that several weeks, because these are, of course, the point is to go into a little bit faster testing. You need to have a large enough chamber, so you have a large enough number of parts, so you can get also the statistics. And the main thing is that you need to have a uniform conditions for every part. So no hot spots, no dry spots, no cold spots, nothing like that. So same temperature and humidity. So similar type of requirements that you should have a proper airflow within the chamber, not excessive airflow, but stable airflow, so that, let's say, all surfaces of all samples should have, let's say, should see the conditions within the tolerances. And quite often, again, here, these are biased, these test samples. So now when you think about pressurized chambers and you need biasing, that kind of brings up one additional requirement for the equipment itself. So if you need to have some kind of wires through the walls, then those also need to be designed in that way that you have pressurized chamber. And then all the parts, including the, let's say, electrical biasing or measurement cables, connectors, they should not suffer from this temperature and moisture. And again, maybe the most important thing here, the water condensation must be avoided. So here I have just one example, which how these chambers could look like. These are from ESPEC. I spec is not paying anything for me. So this is just one example, and then also here are some other versions, maybe a little bit more robust looking. I think these were also from Japan, some companies. But just to show you how these equipment look like. So you can already make a, let's say, see the difference from these chambers to the vice chamber, which I showed you. So quite often these don't have the nice glass window which you can look through, and these are definitely more, let's say, rigid. For example, the door is locked with this kind of a, let's say, very strong mechanical bolts, and that's of course due to the increased pressure. So there's of course the safety issues also which must be included. So maybe the main point from the, let's say, from the equipment point of view is this. So how do you then achieve this kind of a conditions? So what is the way to do, let's say, if you, maybe I will again put the pen. So if the target is to get this kind of conditions, 140 degrees centigrade and 85% relative humidity. So one of the most typical testing conditions in HAST testing. 120, 130, 140. These are the typical ones. And 85% relative humidity. So how you can get it in, this is the test chamber. So how you can get this kind of conditions. So now we just need to remember that relative humidity is function of temperature. So you need to have certain absolute humidity, and then you need to play with the temperature, then you can have relative humidity. So actually how this system operates is that first we have a steam generator. So basically we form a saturated water stream, steam, meaning that now in this case, the temperature of that water steam is 134.3 degrees centigrade. So the relative humidity is 100%. Yeah. And we inlet that saturated, let's say, steam into the testing chamber here and heat it up. So basically, now we have, if we would look back onto these tables, we would see that now here the absolute humidity refers to this relative humidity and that temperature. So when we have 134 degrees centigrade, 100% relative humidity, then we just heat it up with resistive heating or whatever. So then we can end up having this kind of conditions. So relatively simple thing to do. Of course, we need to be sure that again then the conditions are uniform here in the testing chamber and so on. So we need to have also more safety features. So if, for example, our heating system goes crazy and starts heating and heating and heating, so the power is constantly on, then of course what is happening is that the pressure starts to increase, and then we have an explosion. If we don't have this kind of a exhaust mentality here, which then starts letting the extra pressure off. So of course, from, let's say, from safety point of view, these HAST chambers are much more challenging than the 85 chambers. So I think I've already mentioned these things. So safety features, very strong chambers, bolt down doors, and so on. And once more, the point is to compare things or define the acceleration factor if we are sure that the failure mechanism is not changed. And quite often here we use the same approach as what we use for HAST testing. So again, maybe just a very short recap. So we had these Weibull graphs. So here we have the time, and here we have the, let's say, the failure probability or whatever. So 100%. So what is the fraction of devices which have failed? And then we had different conditions. So we had the, okay, that should be a straight line like this. So this was the use. So this was the ALT, accelerated live test, and this was the highly accelerated live test. And now if the slopes are identical, then we can define the acceleration factors, which are these values here. The same approach, it could be used in HAST. So basically we have here the highly accelerated stress test, and we have the 85. Sorry, I'm not sure if you can see anything, but this is the 85 test. So instead of trying directly calculate the acceleration factor from here to here, we can use this ALT test as a, let's say, intermediate or confirmation step in between. So we calculate this or compare that there's a, let's say, reasonable and verified acceleration mechanism between these two tests, less accelerated and more accelerated, and then we have also the same here, the use conditions, so non-accelerated and slightly accelerated. And then we could basically, based on this result, so 50% of the products have died after this time. So this is the testing time, and we could multiply that one with the acceleration factor. So this is the field time when half of the population have failed, or 63.8% in Weibull, or whatever is the number. It could be like in, I think in Jonas's example in this bicycle test, they used this 5%. So they compared when was 5% of the products failed, because that is kind of from that application point of view, it is critical to know that number, if I recall correctly. Okay, so this is again a very confusing picture, but I hope that now you can get the big point at how similar these things are and what is the way of approaching the let's say the testing. Okay. And now finally, few let's say equations. So as I already mentioned, we have this PEX equation, which has let's say different versions, several different versions. If you just put in the Google PEX acceleration transform or PEX acceleration factor, then you have different forms of that let's say equation. But basically, whatever it is, it states that time to failure is somehow proportional to this Arrhenius part, so the temperature part, and then relative humidity power something, or it could be relative humidity in exponent with respect to some similar type of activation energy, whatever it is the form. So of course we need to, let's say, define empirically what these constants are. And in fact, this guy, Michał Sinadurai, is I think it's the same guy who is still very, very active in European conferences. I have never asked him. I have met him several times, but I think at least the name is the same and topic is the same. So he published already, what is that now, 25 years ago, a survey. He went through about 90 different cases where this kind of different temperature, humidity conditions have been compared to field conditions and the acceleration factors. And when we are talking about moisture absorption in organic materials, most of these cases the moisture was absorbing to epoxy-based polymers, which are of course the most common in electrolytes. So he kind of concluded that this exponent should be close to 3, and the activation energy is about 0.9. So in a few slides back, we used the assumption that this is 1 electron. So, and also he derived this kind of an let's say equation that here is the let's say if you want to simulate a certain lifetime, that value is here. And so what is the required testing time? So same thing, but if your customer asks that, okay, please make sure that in our conditions these products will withstand 10 years, then you can play with the testing time and testing conditions. And again, based on this simple equation, I made an Excel. Let's see if this works or not. Okay, I hope that you now see the Excel. If not, then please shout. So what is here is basically just,
I can't see it.
You can't?
No, it's still in the PowerPoint.
Okay, let's then take another approach. Stop share. Share again. What about now?
Yes.
Okay, good. So basically, here are basically behind this table is just the previous equation. So here we have, let's say, point here is that we can either see what is the required testing time or the let's say final lifetime if we have certain test time and certain test conditions. Okay, sorry, maybe I'll need to put it a little bit smaller. I hope that you can still see it. So here we have the test temperature. Here we have the use temperature. Here we have the test relative humidity, and here we have the use relative humidity. So if we now assume that we are using a product in conditions where the average temperature would be, let's say, 30 degrees centigrade, and average relative humidity is 50%. Then if we use this 85-85 test, then the lifetime, let's say, okay, now test time 1000 hours means that it is about 32 years. Looks quite nice. But if we, for example, start, let's say, decreasing the testing temperature down to 50, then of course this about 1 month test is let's say, indicating only less than 4 years testing time. So this is just showing how fast, how this, let's say, acceleration happens when you either change the relative humidity or relative temperature in the test, and you have certain conditions. Or then if you want to simulate basically the same thing, that if you want to simulate, for example, lifetime of 10 years, so here we have 10 years, this indicates what is the test time in hours if we have certain conditions. So now if the use conditions are 25 and 50, so 25 degrees centigrade, 50% relative humidity, and we use testing conditions which are 35 and 60, then the acceleration is really small. So our testing time is 24,000 hours, so it's more than 2 years. So the acceleration factor is just maybe 3, or so this is almost 3 years. So you can see that if we want to have relevant testing time, we either need to increase the testing temperature, let's say to 70, and then we already from 24,000, we decrease the testing time to 2,400. So this is now 3 months, which could be maybe sensible. But if we cannot increase the test temperature not more than 60, then maybe we need to increase the relative humidity up to 95, and we are getting then the only what is that, half a month or something like that, 20 days, less than 20 days. So this was just a point that, okay, if you, maybe I will now stop share and start sharing again, and now should be most probably this one. And again, maybe Anton, if you shout if you don't see the slide now in the presentation mode.
It's in presentation mode.
Okay, thanks. So jump to the next. So this is another way to, let's say, utilize the same let's say data. Why I have composed this kind of a diagram. It was coming from the, let's say, one of the Finnish paper manufacturers. They were kind of thinking about of making these RFID tags. So now you already know what is the company, but it's already so many years back that I don't think it's confidential anymore. So they wanted to, let's say, they asked that, okay, if our customer wants to verify that this product RFID tag, its lifetime is 10 years, and the relative humidity in the use conditions 50 degrees centigrade, and temperature, average temperature, use temperature is 25. So what kind of, let's say, testing conditions and types we should use? And now I have here 2 lines. This line here having the purple color, that is indicating the test time needed if the test, let's say, relative humidity is 60%, and here on the x-axis we have testing temperature. And this dark blue color indicates that if we are increasing the testing temperature from 60% up to 85%, so we can see the acceleration here with the same temperature. So this is just how one can estimate the effect of temperature and humidity combined effect in the acceleration. So maybe to conclude, this one is that here is a table. Maybe if you now can have some kind of picture in your head, which is, let's say, states roughly these values. So here the point is that we start from the standard 85 test for 1,000 hours, which it says here it's 6 weeks, but it's not 6 weeks. I don't know how they have calculated. I think it's less than 5 weeks, but anyway, something like that, in that order of magnitude. And then if you start going to HAST testing, so you start increasing the testing temperature and you keep the relative humidity at 85, then how the testing time goes. So from several weeks down to less than a day in 140 degrees. And then if you transform those results to, let's say, jungle conditions, meaning that you have really high relative humidity and, let's say, temperature, which is typical from the nature without any power losses or anything like that, then you see that this 1,000 hour test would refer to something like 10 years. But it would also, if we think about now where we are sitting, this room, it would mean that 1000 hour means 400 years. Okay. And we could accelerate this testing by increasing the temperature. So we would go with these conditions, we would go less than a day. So now the question is, which is relevant? So from here to here, maybe it's quite easy to accept that this acceleration, at least for most of the materials, should not be over accelerated. But is it really reasonable to assume that you can simulate 400 years of lifetime with tests that takes less than a day? Maybe, most probably not. But is this even relevant? Of course not. So this is the big question which we also always need to ask, how much we can accelerate. But if we know let's say the physics of failure, and especially if we have some kind of a model equation which is failure physical, like Arrhenius is, anyway, we know that it's truth in the nature. We may have many other things which are affecting on that. But if we know the activation energy, then we know how temperature affects on that specific mechanism. Then we can utilize these tools efficiently to either test and see what would be the lifetime, or vice versa. If we have a certain lifetime target and we know the conditions, then we can play with the testing parameters so that we can have reasonable testing times. Because quite often, for example, this temperature, this is material dependent. So there might be some critical factors, some critical materials in our, let's say, device. So for example, we shouldn't exceed or even go really close to the glass transition temperature. And then it might be that, okay, you can go only up to 85, or you can go only up to 70 degrees. And that means that then, okay, what you need to do, you need to try to have the acceleration from the relative humidity. So how close you could, for example, go to 100%, maybe 95, and that would be your option then, or solution. Okay, what I wanted to kind of highlight here, that maybe now you have formulated this already, this kind of a conclusion, that when we are talking about reliability, especially accelerated reliability testing, we are quite far from so-called exact science. So all the equations, what we have, the models, they are models. They are valid only within the certain boundary conditions. And these boundary conditions might be the stresses. So this model, what we have, is valid in a certain temperature range. It is valid in a certain humidity range. It is valid in whatever stress range, or it is valid only for certain materials. So it is valid for only polyimide. It's not valid for epoxy, or vice versa. Or it is valid for most of the organics, but it's not definitely not valid for ceramics or glasses or something like that. Or for metals, it is applicable for certain types of copper, like electroplated copper, but it may not be even applicable for other types of copper, which would be, for example, let's say mechanically cold deformed or annealed or whatever, which have completely different microstructure. So some fatigue models might be like that. Okay, so that kind of now concludes the part of the discussion of testing in hot and humid environments. And then we have a little bit more time, so we can start let's say, including the effects of corrosion. So let's start with let's say, formal definition. Again, it's always good to have the kind of formal definition. So what is really corrosion? And this is now coming from this ISO and our national standards. So corrosion is a physical-chemical reaction between a metal and an environment that can change the properties of metal and can thus cause failure of the metal, environment, or technical system. So, okay, sounds nice, good. What is, let's say, important part here is that even it's a formal definition, it's limited to certain material group. And now when we start thinking, yes, that is kind of valid, that when we are talking about corrosion, we are in 99.999 cases, we are talking about metals. So we all know that ceramics, the semiconductors themselves, glasses, they are very, very insensitive to, let's say, typical conditions where we are, let's say, our electronics products are utilized. Of course, we can even corrode ceramics because we can etch them, chemically etch them. But then the conditions are something which is definitely not happening in normal use conditions. There might be some specific cases, like maybe you need to monitor something, measure something from the petrochemical or pulp and paper industry or some other chemical industry where, for example, the pH could be extremely high or low or something like that. But now, if we think about the normal ambience where our electronics is used, then typically the metals are those which are sensitive to those from the corrosion point of view. And then we need to, let's say, understand that the corrosion is not only that specific material itself, let's say, fails. Of course, that's the most typical one, that corrosion is attacking the metal and it becomes mechanically weaker and then it breaks. But it could also be that let's say, the released ions are causing some other problems, like short circuits. Then it's not that copper trace corrosion which is, let's say, causing open circuit. It could be a possible scenario, but maybe much before that, these copper ions which are dissolving are migrating somewhere, let's say, saturating, starting to grow dendrites and making a short circuit. Then it's basically the technical system which is failing. And in some, let's say, extreme cases, it could be the environment which is failing. And where we can see this one, maybe the most logical environment is human body. So the primary requirement in biocompatibility is that the electronics, what you put inside your body, must withstand the let's say, the chemical exposure coming from the body, which is basically the other part here, but also the electronics cannot destroy your body. So the use environment. So from your implantable electronic device, nothing harmful can dissolve into your body. As you saw from, for example, from this implantable pulse generator, which I showed you, there's a large battery inside, and we all know that for example, the electrolytes in the battery, they are really, let's say, toxic. So we must be 100% sure that in any case, let's say, the enclosure of that electronic product which is inside your body cannot release anything from the battery, because that would then cause, let's say, tissue destruction or whatever, poisoning because of the toxicity or something like that. So that's the reason I took this definition, even it sounds very naive and normal, but we should kind of look also what is behind there. So first thing was the metal, and then it was that the effects of these electrochemical reactions, you should look at from different viewpoints. So here is one example. So maybe not that clear micrograph, but here these dark ones, these are copper tracks on a printed circuit board, and basically this greenish stuff here is the spacing between the copper tracks, and these have been now tested in let's say in different conditions, chloride conditions, and conditions where there are flux residues, so soldering fluxes. And what is observed is that dendrites, so these like tree-looking structures, have started to grow. And of course, here, and here, we have a short circuit. So if these two lines are in different bias, 0 volts or ground plus 5 volts, there is a short circuit in between. So this means that now the corrosion has not killed or destroyed the actual material. So this copper line here, maybe the electrical resistivity or conductivity is almost identical to if we compare it to the as manufactured one, because it might be that this is, let's say, 0.1 millimeter wide and let's say 50 micrometers thick, and in order to form these kind of dendrites, we have only consumed less than 1 micrometer from the surface. So basically, from the bulk resistivity, we don't see any effect. So this corrosion has not affected to this material itself, but it has destroyed the functional system by forming this let's say short circuits. Okay, I think this is also quite obvious, but it's good to keep in mind, because quite often you remember these let's say not that direct consequences of these kind of electrochemical reactions. Okay, then a few generic slides on corrosion, and maybe this is the main point from this slide is that if we think about in general now all possible electronic products in all possible use environments. Okay, this is quite arbitrary definition, but you can find different numbers in the textbooks. And typical number is that corrosion, electrochemistry, electrochemical reactions, humidity and impurities have significant effect on the failures, about 1/5 of all field failures. Of course, this value could as well be 10%, it could be as well be 30%, but in that order of magnitude. So definitely it's not less than 1% or something like that, meaning that it is a real problem. And quite often corrosion in electronics becomes a problem if you don't think about it, if you don't care, if you forget it. And therefore, I think it's very important that we discuss on this, because there are countermeasures. You can slow down the corrosion, you can prevent the corrosion with several different ways related to material selection, process control, and design. One thing which we also should keep in mind is that the actual mechanisms, they are identical to what we see in the other world, or let's say structural mechanics, civil engineering, wherever. Just that because of the miniaturization, small sizes, quite often electronic products are more sensitive to let's say corrosion or electrochemistry than bridges or cars or whatever more macroscopic products or devices. And then because this is high number also because we know that corrosion has these indirect effects. So as I already mentioned, it's not that it needs to be so that corrosion itself destroys the actual material, but it can assist also other failure mechanisms like stress corrosion or corrosion fatigue are of course in mechanical engineering very well known let's say phenomena, where something like let's say cyclic loading, if this would be steel or aluminium or something like that, and I would bend this in, let's say, dry, clean conditions, it might withstand 10 million cycles. But if we put this metal bar in conditions where there's humidity and chlorine ions, and we do exactly the same bending, maybe the cycles to failure drop from million cycles down to 100 cycles or 10,000 cycles, because the corrosion attacks the surfaces, and we know that fatigue resistance is really dependent on surfaces, because we have these pre-cracks. Typically in fatigue, it takes something like half of the lifetime to form the pre-crack, and then the other half of the lifetime the crack propagates and creates the failure. So if we have a corrosion, it increases the rate of this pre-crack formation, and therefore it can drastically decrease the lifetime under mechanical loading conditions. So that is the point, that you have also these, again, these cumulative effects, which when we are talking about corrosion, again, it might be really completely something else than this these damage accumulation models where you sum up 50% damage and 50% damage, then it's 100% damage and fracture. So you remember that in Jonas's slides there was this damage accumulation, and then I showed it from the Juha's doctoral thesis, these let's say approaches that how one should consider the microstructural effects in order to really understand these kind of combined loading conditions where this 1 + 1 is not 2. 1 + 1 might be even 10 in some cases, like stress corrosion or corrosion fatigue. Okay. So just that when we are talking about corrosion, we are talking about electrochemical reactions, and basically the, let's say, the key terms which we need to understand is that we need to have an electrochemical cell. So what it means that we need to have in practice a liquid. Some specific cases this liquid could be liquid metal or something like that. Typically it's some kind of an aqueous solution, so water containing something. So it's pure water is not enough. If we think about just extremely high purity water, that is not an electrolyte because it does not have electrical conductivity. But immediately when something is dissolving there, then it becomes an electrolyte. So you need basically an electrical contact, so two materials which are in contact physically. Then you have the electrolyte which is conductive, and then you have two materials which are have different nobility. So they in electrochemical series they are different. Then the less noble, that becomes anode, which starts to dissolve, and the other one is cathode. And now, depending on if we are, let's say, talking about corrosion, or let's say electrochemical plating, which is typical manufacturing method in electronics. Basically, we are talking about same thing, but we just control them different. Corrosion is uncontrolled typically, and plating is the same mechanism, but it's a controlled one. So what we know is that our corrosion products can either grow from the anode, like here. This is a plated through hole in printed wiring board, and around that plated through hole, so the electrical connection between top surface and bottom surface or inner layer in printed wiring boards. So this is picture from the top. So you see that around this hole, there are these tree-looking structures, which are, at this case, copper sulfates. So it's a copper reaction product with sulfur. So we need to have a sulfur coming somewhere. We need humidity, and now we know that this is anode, because the reactions products, they grow on anode. So we would be talking about this. If this would be pure copper, then most probably the adjacent plated through hole here would be the one which has the plus potential. This would have the minus potential, and the copper ions would dissolve here or here and migrate to here and start growing on a cathode and forming these. Then it would be pure copper, and that would, let's say, correspond to copper plating, copper electrochemical deposition. There, of course, we want to deposit pure copper, and it's depositing on the cathode. Anode is our source of material. In corrosion, it's like the other way around. So anode is the poor guy who is dissolving. So when we think in general, this is again a diagram which I stole from PTT book. So if we talk about in general corrosion of electronics, these are the typical factors which affect on the corrosion. So of course we have these, let's say, normal, quite self-evident things like impurities coming from our use environment, but also we can have, for example, the effect of solar radiation. Why? We have discussed this already several times, that the UV radiation can decompose our polymers. When the polymer chains are getting looser and looser, more moisture can penetrate in. You have higher moisture content, of course, then you have a higher probability of corrosion. Can even have effect of different types of things from organic world, like fungus growth, which themselves can produce organic acids, which can accelerate the corrosion, and so on and so on. Very common source of impurities, even in the modern electronic products, are soldering. So the soldering process where you need fluxes. So fluxes are these chemical aids which enable wetting. So reducing the surface oxides and cleaning the contaminants. Allow that when you have a solid surface and you put a drop of liquid on top of that, our solder, so that the liquid spreads on top of the solid and forms, let's say, chemical bonds. So this is what fluxes are helping, so reducing the surface energy, or increasing the surface energy of the solid, so that maybe some of you remember Young's equations or the surface energies of these ones. So in order this liquid drop to go that direction, we need to have high surface energy solid gas. So if this is oxidized, then of course energy is minimized, so this driving force is smaller. But if we have here copper oxide, and then we have a flux containing chlorine ions, this chlorine reacts with oxygen and leaves metallic copper surface, which have high surface energy that allows the wetting, the spreading of the liquid solder. So that is the basic reason for fluxes. And these fluxes typically contain something, or always contain something aggressive, ions, because they need to react with the oxides and other surface layers. So also possible that you get residues. And these are one of the most harmful things in electronics. So there's lots of tricks, no clean fluxes, solvent cleaning, these conformal coatings to slow down the moisture, and things which you can, let's say, again, minimize the effects of flux residues. Other residues, so for example, in printed circuit board manufacturing, we have lots of chemistry. It's full of wet chemistry, and it's always possible that you get residues. There's lots of acidic parts, base parts, rinsing waters, and everything, which can be stuck somewhere in internal structures and then later on cause some problems. And then, as I have already mentioned a few times, we also have the organic materials themselves. They contain more or less ions. So if you think about just normal epoxy, it's not just hydrocarbon. It contains also at least certain amount of chloride in the ppm level, so parts per million level, but still at certain circumstances, conditions, even this small level could be very, very critical from the reliability point of view. And if you want to purchase more clean epoxies, then you need to pay more money. They are much more costly, expensive, these cleaner materials, because it takes effort for the manufacturer to manufacture materials where the, let's say, typically halide, so chlorine, fluorine content is very, very low. Okay, and then basically we end up in the same situation that we have the same things. These were the, let's say, impurities which we discussed in the classification of environmental conditions. So these are also really typical coming from the product itself or coming from the use environment. And therefore we are interested in this. And these then cause mechanisms, different corrosion mechanisms. So we have 5-minute time, so maybe we'll let's say quite quickly go through corrosion mechanisms, just you to see that there are basically 4 different mechanisms. And now I'm not going to talk about anything about the fretting corrosion, because that's kind of a dry corrosion, oxidization-based corrosion mechanism, and it's especially relevant in connectors. So I will show this one later on. But now, very shortly, what are these 3 main corrosion mechanisms when we are talking about wet corrosion? Chemical corrosion, galvanic corrosion, and electrolytic corrosion. This is something that I have asked quite often in the intermediate exams, because this is basically important thing, but also very simple thing. So chemical corrosion, we can basically just say that it's you have a metal, a surface, and then you have an environment, and there will be a chemical reaction between the surface and the environment. So for example, if you are in Otaniemi, you go to the Dipoli, and you look let's say the window frames in Dipoli. When that building was manufactured, it had nice shiny copper there, but now everything is completely dark and black. I hope that they still have this same after the renovation, but at least before the renovation. So basically, when you put copper sheets outside, the copper will react with the sulfur and chlorine, which is in the air, normal, let's say, air in the normal conditions outside, and it will turn eventually black. So that is a chemical corrosion. Just a reaction between surface and environment. And there's let's say, of course, huge amount of different environments and different case examples. And definitely now don't even try to remember this one. This is just to show that in one of the books, we can have this kind of models for chemical corrosion. In fact, here this basically the equation shows the critical quantity, so how much impurities you can allow in the let's say in the ambient in order to, let's say, avoid corrosion. And here inside this equation you have several different things: corrosion rates, gas densities, some enthalpy values, activation energies, vaporization enthalpies, and so on. Just to show that, okay, the equation is complex, it looks like a very physical, is it really? It also have, let's say, these kind of constants which are semi-physical. So let's not go on that. One more minute so we can quickly check the most important thing is the galvanic corrosion. We know that in our steel roofs, we always use zinc on top of steel because we want to have the less noble metal on top of more noble metal. And therefore, if we get a scratch in the roof, this less noble metal starts to corrode, which there's high surface area. In electronics, we typically always have less noble metal is underneath the more noble metal. And now, if we have a defect, then the less noble metal becomes anode and the surface area is more. So what it means is that because we here in a cathodic reaction, we let's say consume as much electrons as is formed in the, let's say, corrosion dissolution reaction. So it means that the currents must be equal. If this surface area is much smaller than this one, then the current density, which is also directly proportional to corrosion rate, is very high here. So locally, this kind of a less noble metal is starting to corrode fast underneath more noble metal. And now, of course, we have the electrochemical series, which define the driving force. So how far the materials are, the higher is the driving force. And then this situation can also be coming from our electronic circuit. So we just have copper and copper, but one is plus, one is 5 volts, one is 0. Then there is already potential difference, which drives the corrosion reactions.